As soon as the fan starts, it immediately begins running at a very high speed. The compressor has also started. Now look closely. The fan speed increases and then it stops. Actually, it doesn't completely shut off right away. Once it starts, it doesn't stop immediately. Instead, it gradually slows down. After that, you can see it starts running again. So in this way, there is clearly some kind of issue occurring in the system. And to test this, you can see that I have installed a heatsink on top of the IPM module. This is my dedicated testing fan, which I keep with me, specifically for diagnostics. This one is the customer's fan. Now we will check the circuit using the customer's fan to see how the PCB responds. Now, after connecting the customer's fan, I am turning the system on. And the fan has started. But in this one, it is not giving that high speed. The fan is running completely fine. There is no fault of any kind in it. The compressor is also running at the correct speed. It is operating completely normal here. So I will turn the system off. So this is the inverter outdoor fan circuit, which has pins numbered from 1 to 7 on its connector. Out of these, pins number 2 and 3 are non-functional, while pin number 1 carries 320 DC volts, whereas pin number 4, as you can see here, is directly connected to ground. Pin number 5, as you can see here, is directly connected to 15 DC volts. However, you can also notice a small circuit section attached to it. When 15-volt DC comes through this line, it first passes through the L800 inductor installed here. What happens is, when the 15-volt DC moves from this side to the other side, it can move very quickly and with a high surge. This inductor is installed to control noise, so that all types of electrical noise can be filtered and eliminated at this point. Then here, there is a main component standing in this section that prevents the 15 DC volts from collapsing. That component is C802, the capacitor installed here. This capacitor is rated at 100 microfarads and 25 volts. What happens is that when the DC voltage reaches this point, the capacitor charges and discharges accordingly. In this way, it also performs a filtering function, so it is actually performing 2 to 3 functions at the same time. Then, there is another function here, which is performed by the 24-volt Zener diode installed at this point. What it does is that if, for any reason, the voltage here rises to 24 volts or higher, for example, 25 volts, this diode becomes active. If 25 volts come in, the voltage up to 24 volts will remain here, but anything above 24 volts will pass through the diode and go to ground. So this diode acts as a protection device to keep the system stable. Now let's talk about pin number 6. This is the VSSP pin. Through this pin, the fan is started and controlled during operation. The circuit connected here is responsible for performing all these functions. In this circuit, first there is an NPN transistor installed, and then there is also a PNP transistor installed. Now, this NPN transistor is numbered Q800, and the PNP transistor is numbered Q801. Inside both of these transistors, there are built-in resistors. These resistors are 4.7 kiloohms each. Both of these are bias resistors. They are installed here to keep the transistors protected and operating safely. How they work, I will explain to you further ahead. After that, on the emitter of the NPN transistor, ground is present, while on the emitter of the PNP transistor, 15 volts DC is present. Here, resistor R801 is installed, which is a 1K resistor. This acts as a current-limiting resistor. After that, there is another resistor and a capacitor connected here. The 560 ohm resistor works as a pull-down resistor, while the capacitor C800 is installed to control all kinds of noise and fluctuations. Now, how does this whole function actually work here? Because these transistors are charged once and then discharged once. Now, how this charging and discharging happens, I will explain it to you. When the microcontroller generates plus 5 volts on pin number 2, it will turn on. This 5 volts will go to the base of the NPN transistor. The 4.7 kiloohm resistor connected there acts as protection and limits the current going into the transistor's base. This transistor will turn on. When it becomes active, the ground present at the emitter will move to the collector. Once ground appears at the collector, it will be connected to the base of the next PNP transistor. It is connected to its base, so the function here will be the same. The resistor connected at this point will act as protection and provide current limiting. As soon as ground is applied here, the PNP transistor will activate. Since 15 volts are present at its emitter, those 15 volts will move toward the collector. When the voltage moves to the collector side, there is again a current limiting protection resistor connected in the path. As a result, the 15 volts will reach pin number 6, the circuit function will be completed, and the fan will turn on. When these transistors are charged once, it is also necessary to discharge them again. This improves their overall performance and ensures proper switching. Now what will happen is that as soon as the 5 volts are turned off here, even for a few nanoseconds, this resistor will become active. This resistor is a pull-down resistor, and since ground is present on one side, the ground will move toward this side. As soon as the ground moves here, any floating voltage present at this point will be pulled down to ground. Once it is grounded, the transistor will turn off completely. When this transistor turns off, the ground path that was flowing from emitter to collector will also stop on this side. Then what happens is that the resistor connected here becomes active. Since 15 volts are standing at this point, and there is also a pull-up resistor connected, those 15 volts will move toward this side. If there is any floating ground present here that could keep the transistor turned on, it will be overridden, dumped by the 15 volts. As a result, 15 volts will become active at this point. This makes the base positive, and when the base becomes positive, the transistor turns off. So the 15 volts will stop flowing from emitter to collector, and the signal will be turned off once. Then, when the microcontroller supplies 5 volts again, the whole procedure will repeat. In this way, the process keeps running in a continuous loop. But I forgot to mention one more important point here. When the 15 volts stop coming to this point, floating voltage may still be present here. In that case, this resistor will act as a pull-down resistor. The ground will move toward this side, and if any floating 15 volts are present here, they will be dumped to ground. Once those floating voltages are removed, the signal going to the fan will completely disappear. As a result, the fan will turn off properly and the signal line will be fully cleared. Now let's talk about pin number 7. This is the feedback pin. When the fan is running, the microcontroller receives whatever data or pulses are coming from the fan through this pin. Based on that feedback, the microcontroller then adjusts and outputs signals again from pin number 2 accordingly. To control this process, a small circuit is built here. Let me explain it. There is a resistor labeled R803, which is a 10 kilo ohm resistor. It works as a pull-up resistor. There is also a component labeled D600, which is a dual diode package. In this package, the anode of one diode is connected to this point. The cathode of the other diode is connected to the other point. This arrangement helps in signal conditioning, protection, and proper feedback control to the microcontroller. Similarly, there is R804, which is a 1 kilo ohm resistor. This is called a current limiting resistor. In the same way, C801, capacitor 801, is installed here for filtering purposes. Now, what happens here is that when a ground signal comes from the fan circuit to this point, 5 volts are already present on the pull-up resistor. Those 5 volts are pulled back and the entire point becomes ground. Once it becomes ground, a clean signal is sent toward the microcontroller. Before reaching the microcontroller, the signal passes through filtering via the capacitor and current limiting via the resistor, ensuring the signal is stable and protected. If exactly 0 volts are coming here, that means the diode will remain inactive. This is because a diode needs approximately 0.7 volts difference in the case of a silicon diode to become forward biased and conduct. So, if the voltage at the ground point rises above 0 and reaches around 0.7 volts, that portion above the threshold will be clamped, conducted through the diode toward ground. As a result, a clean signal will be sent to microcontroller pin 17. The ground signal from pin number 7 will stop. This resistor will become active, and the 5 volts will come to this side. When the 5 volts come here, another 5 volt signal will go toward the microcontroller. Now what will happen if for some reason the 5 volts increase and become 5.7 volts? Then 5 volts will go in that direction, but the extra 0.7 volts will go to this side, because this diode requires 0.7 volts to activate. So here there are 5 volts present, and there are 5 volts present. As soon as the voltage difference, or potential difference, becomes 0.7 volts, the 0.7 volts will move to this side, and the 5 volts will move to that side. In this way, this diode performs a very important function. It keeps both sides of the system safe so that the microcontroller does not receive a signal higher than 5 volts. Now we will check these fan circuit points using a multimeter. First of all, I will supply power to it. Right now, I have not connected the fan connector here. We will only check how the main supply is coming at this moment. Now, first we will check pin number 1 and pin number 4. Here we are getting 338 DC volts. Now if we check pin number 4 and pin number 5, we are getting 15.44 volts. And then we will check pin number 6. Here it is 0. That is completely fine because the compressor is not on yet, so no voltage will appear here. Now let's check the feedback. Here we will get 5 volts. That is okay because we saw that 5 volts are present on the pull-up resistor, so those 5 volts will also be present here. Now we will wait for a while until the compressor starts. After that, we will be able to see voltage on pin number 4 and pin number 6. Until the microcontroller turns on the voltage, no voltage will appear here. Right now, the circuit does not know that the fan is not connected. So for a short time, the voltages will turn on, and then they will stop coming. This is because the system will try to start the fan and expects feedback to determine what condition the fan is in at that moment. Look at this. As soon as the fan started, it began from around 2 volts, and you can see that 4.9 volts have appeared here. The maximum voltage is about 5.5 volts. These maximum volts were released by the microcontroller, which is quite high, and now you can see it has turned them off. After a short while, it will try again. This means the circuit is performing properly because it is trying to turn the fan on in the correct manner. Now we will turn the system off once. Now I will connect the fan connector here, which I made for testing. You can see that I have installed another connector inside it, so that I can also test it in other models. Now what we need is the main voltage between ground and VSP, so we will take it from this yellow wire here. I have already connected the multimeter probes to both points. I will turn the unit on. The outdoor is now on. Now I will turn the system on using the remote. Let's turn on the multimeter. Here, the first thing we will analyze is the VSP voltage. We will observe how the microcontroller provides voltage here when the fan is connected, and whether it becomes disturbed or not. Because when we did not connect the fan connector, the VSP was behaving completely normal. The fan started, and the voltage opened from 2.9, then 4.5, and then fully to 5 volts. In fact, it even went slightly higher. That is why the fan is running faster than its normal speed. Now let's check whether its feedback is coming or not. Look, the fan is turned off again. Now we need to see whether the feedback is being properly generated or not. In a short while, it will turn on again. The fan has turned on, and here we are getting 5 volts only, and there is no fluctuation here. This means that we are not receiving the fan's feedback at this point. Because of that, this problem is occurring. If feedback is not received, the fan cannot be controlled properly, and the microcontroller will consider it either disconnected or faulty. Now we have installed the customer's fan here, and we will connect its connector to the PCB. We already know that the VSP voltages in the circuit are completely okay. So now we will check the feedback line to see what reading we get there. Let me connect it here. Now I will turn the unit on. We'll switch it on using the remote. Now look here. The 5 volts are coming from the pull-up resistor. So, these DC volts have disappeared. There should not be any voltage present on the VSP at this time, and this condition is completely correct. The feedback line that was previously sitting at 5V, due to the pull-up resistor, is no longer stable. This indicates that when the fan is connected, something is affecting the feedback line. Either the fan is pulling the line low, shorting it, or failing to generate the proper feedback pulses. The fan has started, and you can see that when the fan started, 2.4 volts are being output. Instead, it shows an average voltage value. So when the multimeter shows around 2.4 volts, it means the signal is switching between high and low states. The meter is simply averaging the pulses, which confirms that the feedback signal is being generated correctly. But when we see a steady 5 volts, it usually means there are no pulses at all. That indicates there is no feedback signal coming from the fan. So in this case, 2.4 volts reading feedback pulses are present, fan is working properly. This confirms that the current fan is completely fine, and the previous fan had a problem because its feedback signal was not being generated.
Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.